Okay, as the first bit of probability, a random variable is one whose value cannot be predicted but is determined by the outcome of an experiment. Example, throwing 2 dice. So a random variable is one whose value cannot be predicted but is determined by the outcome of an experiment. So if I toss a coin or if I throw a couple of dice, I can't tell what's going to happen. Okay, I can't say yes, 2 threes are going to come up on those 2 dice. Okay, I don't know that. So it cannot be predicted, but it's determined by the outcome of experiment. So in other words, I want to find out what comes up on a dice. If I throw it 5 times, or a pair of dice 5 times, I've got to do an experiment to look at that. If I want to toss a coin 10 times and see what happens, I've got to do an experiment, but I cannot predict. So that's a random variable. I think we know what the word random means, chance. And a variable is something that can change. So with probability, this year it's all about these random variables, getting data or doing experiments to work out probabilities, the chance of things happening. All right. Just some notation on random variables. They're usually expressed as capital letters, X, Y, and Z. The value they take on is represented by lowercase letters, lowercase x, y, and z. That will make more sense later in this presentation here when we actually start doing some problems. So don't worry too much about that at the moment. Right, there's 2 types of random variables. This is the first really important thing we learned today. Discrete and continuous. Discrete random variables deal with number or size generally. Possible outcomes are able to be counted. Now, they don't necessarily have to be whole numbers, and shoe size is an example of that, okay, because shoe size can be 9, 9.5, and those sorts of things. But they're usually whole numbers, okay, but they can be counted, okay. So if I toss the coin 10 times, how many times do I get 6? How many times do I get tails? 6, okay, so it's a definite number. It can be counted. The possible outcomes are able to be counted. So they're discrete. They don't take on long decimal values. Okay? And that's the contrast here with continuous random variables. This deals with quantities that can be measured, that can be 10.357 seconds. Okay? That's why measuring times for 100 metres aren't discrete, because it's not, you don't say they ran 10 seconds, because 10 seconds could mean a whole lot of things. Okay, it could be 10.3, 9.7, right? When you're measuring things, okay, there can be a range of values. They're not whole number counted values. And things like that are mass, height, and time. Now, you might say, okay, well, we don't say that we're 67.358 kilos. We just say we're 67 kilos. I understand that. But technically, things like mass, weight, height, and time are examples of continuous random variables. They don't take on whole number counted values, okay? They can be a range of things. My height is 175.3 centimetres, something like that. So they're not nice whole number counted values. They're continuous. And we deal with those later in the year when we do normal distribution. So we're really, in this first couple of units of probability, looking at these discrete random variables. Okay, so according to those 2 definitions, discrete and continuous, let's look at some scenarios. So the number of goals scored at a football match, is that discrete or continuous? It's discrete. Discrete as the goals can be counted. Okay, so you score 2 goals, or you score 3 goals, or you score 4 goals, or 5 goals. You don't score 2.378 goals. So they can be counted, they're discrete. The height of students in a maths method class, okay? Height, now I know you will think, but you just round off to 175 centimetres, stuff like that. But as soon as you're doing height, it's continuous, as height can be measured. So as soon as you start measuring something, okay, with a measuring tape or a stopwatch, okay, it's continuous. It can take a range of different values, not just discrete whole number values. So that's continuous. Shoe sizes, what I mentioned before. Shoe sizes are discrete. The number of shoe sizes can be counted. So you 9, 9.5, 10, and 10.5, and you go up. That's an example of discrete ones, or a discrete example, not necessarily whole number values. It's an exception. Most of them are whole number values. But your shoe size is not 10.35. It's 10 or 10.5, and then it's 11, so on. The number of girls in a 5-child family. Discrete or continuous?
Discrete.
Discrete. Okay, the number of girls can be counted. Okay, so in a 5-child family, there's either 0 girls, or 1 girl, or 2 girls, or 3 girls, or 4 or 5. Discrete. The time taken to run 10Ks. Continuous. It's a time thing. Time must be measured. Right, so that was a little exercise in getting familiar with what's discrete and what's continuous. And now, having said that, discrete is what we're talking about early on in the year. Continuous comes right at the end of the year. All right, here's an example. Let X, looks very wordy, but it's not too bad. So let X represent the number of tails obtained in 3 tosses. Okay, so you're tossing the coin 3 times. So X is the number of tails. So it's the random variable, capital X. Draw up a table that displays the values the discrete random variable can assume, can take on if you like, and the corresponding probabilities. Okay, so if I toss the coin 3 times, what are the possibilities for the number of tails I'll get? What are the different possibilities?
You get wait, do you mean what the chance is? Or what
No, not the tails. What are the outcomes?
You get like head, tails.
Yeah. I'm just focusing on the number of tails. So how many tails could I get out of the 3? 3 or? None or?
1
or 2. So they're my outcomes. Either no tails at all, 1 tail out of the 3, 2, or all 3 are tails. So they're my possible outcomes there. And you might have seen these before. Who's seen a tree diagram before? Okay, a lot of you have. And that's how they're constructed with the different probabilities. Now, I haven't written in the probabilities here because they don't change. We usually don't if they're 50-50 situations, but we know that it's a half if it's an unbiased coin. It's a half a chance in all these branches, 1 in 2 chance. Just point out at this stage that probabilities, if you've seen them before, can be expressed 3 ways. They can be expressed as a fraction, so a 1 in 2 chance. Okay, they can be expressed as a percentage, so 50% chance. Or they can be expressed, what's the third way? Does anyone know? As a decimal, so it's a 0.50 chance. Now, we don't use percentage as much, we sort of stick to those 2, but all those 3 can express the same thing, a probability of an event. So there you go, so there's my 3, tossing the coin 3 times. Each time we've got a branch, it's another toss of the coin. So in other words, if we get heads first up, the second one could be heads or tails. If we get heads and heads, the third one could be heads and tails, and so on. You can see how it works out. There's my outcomes. All right, so this leads us to what we call a probability distribution. Okay? Now, this is the difference between the capital letters and the small letters. So the capital letter here is, okay, the probability of X equaling X. So that is the random variable. That is tossing a coin 3 times. That's what that is. The little x are the actual outcomes. And that's the question I was asking Lockie. What are the outcomes? So there's 3 values little x can take on. There they are on the table. Okay? 0, 1, 2, 3. So the capital X is the actual variable itself, tossing 3 coins. The little x is the value it takes on, either 0, 1, 2, or 3. Now let's place in the probabilities here. Which is the only outcome there out of the 8? You can see there's 8 down there, from top to bottom. Which is the only outcome which gives me 0 tails? Heads, heads, heads. And out of the 8 outcomes, how many out of the 8 outcomes are heads, heads, heads? 1. So it's a 1 in 8 chance of getting 0 tails. How many of the 8 outcomes there have how many of the outcomes there have 1 tail? I answered the question. Oops. 1 tail. Let's have a look. There's 1 tail there, there's 1 tail there, and there's 1 tail there. So how many out of the 8? 3 out of the 8 have 1 tail. Is that all right? Yep, see that? How many outcomes have 2 tails? 1, 2, 3. So 3 out of 8. And there's only 1 outcome that has 3 tails down the bottom. So 1 out of 8. So that is a probability. I'll write this down. That is a probability distribution. Probability distribution takes all the different probabilities, all the different outcomes and gives them a probability. So there we go. Probability distribution. Pretty easy. They can be then graphed, and I've got 3 different types of graphs. They're not super accurate, but you get the idea. It's almost like goalposts there, aren't they? Those ones. So it's just a straight line. So as you can see that that one's up to 1 on 8, that's 3 on 8, that's 3 on 8, and that's 1 on 8. So it's one way of representing just a vertical line graph like that, or a bar graph like that can do the job. Notice my axes are labelled, the probability's there. So the probability that this event will happen, that's what that means. And the event itself, the outcome itself down there. Third way is just a dot graph, same sort of thing. So there's 3 options there for probability distribution graph. And all that is taking the table and putting it in a graph. Right, what are the characteristics of a probability distribution? Right, each probability lies in a restricted interval between 0 and 1. So we're talking decimals now, right? The decimal version of the probability, or the fraction version of the probability, I should say as well. So any probability you get will always be between 0 and 1. So effectively, what does 0 probability mean? If it's 0 probability, what does that mean? It's
not going to happen.
It's impossible. There's no chance. What's a 1 probability? The other extreme.
It's always going to happen.
Okay, it's definite. Okay, and anything between. So what's a 0.5 probability?
Good night.
Yeah, 50-50 chance. Half and half, right? A 0.25 probability or quarter probability, okay? 25% chance, and so on. But whatever, probabilities are always between 0 and 1. So you can't get a probability of 1.5, right? Because it's not between 0 and 1. It doesn't make sense. You can get anything between 0 and 1, inclusive of 0 and 1. Okay, that's why I've got inclusive down here. But they're always there. So if you see a probability distribution with a number outside 0 and 1, including negatives, obviously, it's not a probability distribution. They always, the probabilities of a particular experiment sum to 1. That is, if you add up, sigma is the Greek sign which means the sum of. If you add up all the probabilities, they equal 1. If we go back to our little example here, way back, what do all those guys there in that table add up to? 1. So it can only be a probability distribution if all the possible outcomes add up to 1. Okay, you can't have missing probabilities. They can't go over 1. So they're the 2 basic characteristics of a discrete, and we've defined that word. Okay, outcomes that can be counted. Probability distribution, so that's the table with all the different probabilities. 2 things are, the probabilities must be between 0 and 1, and they must add up to 1. So, is that a discrete probability distribution? Does it meet those 2 criteria?
Yes.
It does. All the probabilities are between 0 and 1, 0.2, 0.5, 0.2, 0.1. And they do indeed, if you add those together, they add up to 1.0. So yes. Okay? I won't write it down because I've said it on the recording here, but it meets those 2 criteria. What about this one? Yes, all the probabilities are between 0 and 1, and they add up to 1.0. So that's a yes as well. What about this one? No? Now, these can be negative because these are just values that are taken on. Now, that could be losing $1. Now, later on, when we do gambling examples, that -1 could be losing $1, breaking even, winning $1, winning $2. So the x values can be negative. There's no problem with that. It's the probabilities that can't be negative. And they meet the first criteria, that is that criterion. That is, they're between 0 and 1, but they don't add up to 1, do they? Okay, so not equal to 1. So no. How about this one? What knocks it out straight away, Daniel?
Negative.
The negative 0.2. Once again, repeating, the x's can be negative, but the probabilities can't. So no. Just point to that one there. Can't have negative probabilities. All right, on to different types of questions. Find the value of k for each of the following discrete probability distributions. So we've got some x values there, which aren't all that relevant to the question, but we've got our probabilities there. So how are we going to find k, guys?
Add up all the other
Okay, so we know that all those probabilities must add up to 1. So, okay, so we'll set this out properly. Probably going a bit overboard, but we should do that. So we add all the probabilities up. Okay, and they should equal, squeeze it in there, 1. So add up all the ones we've got, so that, plus that, plus that, plus that, is 0.4, 0.7, 0.8. So 0.8 plus k equals 1, and k equals, that must be 0.2. Pretty simple. Is that all right? Nothing too difficult about that. Let's do the next one. Find the value of k for each of the following discrete probability distributions. Okay, so we've got our x values, 0, 1, 2, 3, 4, not relevant. We've got our probabilities, which are relevant, 5k, 6k, 4k, 3k, and 2k. What are we going to do? William, you've got a suggestion? No. What do they all have to add up to? 1. Okay, so would a good strategy be to add them up and make them equal 1? Yeah, let's do that. 5k plus 6k plus 4k plus 3k plus 2k equals 1. Why? Because the sum of all the probabilities has to equal 1. So that means 5 plus 6, 11, 15, 18, 20. K equals 1. K equals 1 on 20. Is that all right? Now, I don't think it asks for this question, but this question could go a step further. Okay, and it could ask for the actual probabilities. So if k is 1 on 20, and we'll do this anyway, if k is 1 on 20, and we've got 5k, what's going to be in there? If k is 1 on 20 and 5k was in there, what's going to be in there? 5 on 20, cancelled down to 1 on 4. Okay, so this one here, 6 times 1 on 20 is 6 on 20, cancelled down to 3 on 10. Next one, 4 times 1 on 20, 4 on 20, 1 on 5. Next one, 3 times 1 on 20 is just going to be 3 on 20. 2 times 1 on 20 is 2 on 20, which is 1 on 10. So in an exam for this question, you'd be expected, I'm sure, to go that step further, to work out k and then put in the probabilities. Last question. Looks ugly, but not too bad once we get into it. Show that the function p of x equals 1 on 100 x squared minus, outside of 6 minus x, where x equals 2, 3, 4, and 5 is a probability function. Alrighty. Now, what are the two criteria for a probability function? The probabilities must be between, and they must add up to 1. Okay, so if we fit both of those here, we've got a probability function. Alright, but it looks ugly, so what do we do? Well, what we do, all we really do here, is we place each of those values there, I might change pen colour for a sec, all those values there into here, one by one. So let's start with P of 2. Just put the iPad down for a sec, a bit easier. So P of 2 is going to equal 1 on 100 times 2 squared outside of 6 minus 2. So you can see all I've done there is put 2 where x is. Equals, so if I multiply across the top here, that times that is 4, times another 4 is going to be 16 on 100. And, you know, we could cancel that down, but we don't really need to. Okay, we can just leave it as 16 on 100. So, same process now with 3. So, P of 3 equals 1 over 100 times 3 squared times 6 minus 3 equals, that times that is 9, times another 3 is 27 on 100. P of 4 equals 1 over 100 times 4 squared outside of 6 minus 4 equals 16 times 2 is 32 on 100. Remembering, we just might bring it over, we've got this guy here from the first one. Let's bring him over to the other side. Let's put him up there, ready to go. Okay, and the last one is P of 5, which we'll squeeze in here. Equals 1 over 100 times 5 squared times 6 minus 5 equals, that's going to be 25 times 1, 25 and 100. Alrighty. So, let's copy all that over so we can see it on the other side. There's all our working. So let's add them up, because if we add them up now, what must they equal for it to be a probability function? 1. Okay, so therefore, if we get 16 on 20, sorry, not 200, 16 on 100 plus 27 on 100 plus 32 on 100 plus 25 on 100. Who's good at their mental arithmetic? We've got 100. Beautiful. Equals 1. Therefore, P of X is a probability function. They're also all between 0 and 1, so it meets both criteria. That's an exam question. Okay. I keep using that term, but so not too bad. It looked a bit ugly. How do I do that? We just had to substitute in 2, 3, 4, 5 and work out our overall answer. Alright, stop the presentation there.